All right, well, that's really cool. Why don't we start playing around with the actual physical properties now that we have this thing working. Let's try changing the length of the pendulum. Let's suppose I make the length of the pendulum 5 instead of 1. We'll go run all of the cells now. Cool. I get very much the same graph here. Let's see, the amplitude for theta is not changing, but the period should be changing. So the period right now we're getting looks like about 4.5. So we had 4.5 for this value of L. Let's try increasing this to 20. So I had a period of 4.5. Now let's look at our period. Oh, I get a much longer period, right? So the period usually goes like root L over G. So it should go up by a factor of, about 2. Yeah, because I multiplied the length by 4, so that goes under the square root. So it should double the period. Yeah, I get about a 9 there. Really cool. Let's see how well that holds up under a large angle Let's see how well that holds up when we go to larger angles. Instead of a theta initial of half, let's go to a theta initial of 1. You notice that the peak crept up here, right? It's no longer at 9, it's closer to 10 now. Let's get that a little bit closer to, let's see, an extreme value to consider is pi over 2, because that's going from here all the way to horizontal. So pi over 2 is just above 1.5, right? Pi times 0.5? Yeah, 1.57. So let's go up to 1.45. I'm going to go up there in steps. Okay, yeah, we're a little bit past 10 in terms of the period here. So that small angle approximation that we usually have is starting to break down. Let's go all the way up to 1.51. Okay, it's starting to creep up there. It's not changing by as much there. But what you'll notice about the theta dot, kind of like what we saw in the algo do, is that it's really starting to look not like a sine anymore, right? Because it's getting much too straight in the middle here to be a proper sine or cosine curve. Here's our trajectory, right? You can really see it's getting this this bowl shape here. Ooh, and my total energy is getting closer to 0 because I'm starting out closer to y equals 0, right? And it's not really significant because you can set that value to be where you want, but it is nice to see that, that the special point is still a special point, All right, let's put this thing all the way up to pi over 2. Pi by 2. I'll need to, I think I can just use pi there since I've done the from numpy import star. Yes, I can. Good. And you see here I'm going to pi over 2, negative pi over 2, and I'm getting just above 10 there. That's really cool. This thing definitely not looking like a sine anymore. This thing is still, it still looks nicely like a sine or cosine. Cool. These are now touching at 0. Really cool. All right, let's try one more thing, and then I want to take a look at the acceleration thing that was troubling me in algo do. I think I figured out the explanation for it, but we'll see if it pans out here. Let's go past pi by 2. Let's go to an even 2 radians. Okay, yeah, this thing's not looking like a cosine anymore, right? It's like the middle's getting a little bit too vertical for it to be a cosine. This thing definitely not looking like a sine anymore. This thing almost looks like a sawtooth function now. And it's actually got a little bit of a wiggle in the middle there. This is what it looks like here, and the bowl is turning into more like a fishbowl. And oh, here's interesting, right? My kinetic energy and potential energy are actually crossing in this case. That's kind of cool. I mean, again, the potential energy is arbitrarily offset, but it's neat that their amplitudes are getting so much bigger than they were before, right? Let's have a little bit of fun. Let's take this all the way up to 2 pi. Right, now if I take it up to 2 pi, it won't move because sine of 2 pi is 0. So we got to go just a pinch before 2 pi. So let's try 99% of 2 pi. So we're going 99% of a full circle, just a pinch shy of a full circle. There we go. These are now looking more like sine and cosine again. Oh, that's interesting. Oh, are they? Oh, I wasn't supposed to go to 2 pi. I was supposed to go to pi. That's right. My mental model of the unit circle has failed me. Okay, there we go. Oh, we actually need to go farther out in time now. Let's change our max time for graphing to, you want to say 50? There we go. Okay, now we are definitely past the small angle approximation, right? Because now my theta, it almost looks like a step function, right? And my theta dot is starting to, this doesn't look like a sine at all, right? That's really interesting. Ooh, my energy graph's looking really interesting. All right, I want to see what this looks like as it evolves over time. What can I do to do that? All right, I want to see what that looks like as it evolves over time. Copy. Let's just make a whole new cell down here, because now I am intrigued. And what I'll do is grab, I just want to look at theta dot, because that's the real, that to me, that's the interesting looking one. I want to see how that evolves as you increase the maximum. So what I'm going to do, I'm going to grab how I did this here. I'm going to copy this. Let's see, I won't need to define that again. All right, we're going to keep all these the same except for theta dot, or excuse me, except for theta. And what we'll do is we're going to put this, let's see, I need to put the plot command under here after I get done with the list there. And now what I'm going to do, I'm going to take this whole thing, the whole simulation. Yes, I'm going to put that inside of a loop, right? So I'm going to have a loop inside a loop, because I want to repeat this thing over and over again. I want to start the problem over and change my initial value of theta. So let's try for theta in range. And you know, let's start all the way at 0, go all the way to 99% of 2 pi, and go in steps of, oh, this will need to be a range, excuse me. And let's go in steps of, let's see, that's going from 0 to 6. Let's go in steps of, let's start with a half. Let's just start with going up in half a radian. So what I'm going to do, so think of this whole thing as one experiment, right? This whole region of selected text is one experiment where I am starting with the pendulum at a certain angle, and I'm letting it oscillate back and forth. And then what I'm going to do is at the end of that experiment, I'm going to graph it, and then I'm going to reset the value of theta to be the next value up. Now, since I'm changing that, I'll need to give this thing a label of initial theta equal to plus string of, okay, I'll need to remember what theta was. So theta is changing over here. So let's call this theta 0. And then we'll say theta list equals theta 0. And we'll say that our theta equals theta 0. So theta is going to be the thing that evolves down here. Theta 0 is my record of what I started out with. Theta 0. All right. Let's give that a try. Let's jump ahead in time a little bit. It took me a few minutes to find a couple of mistakes I made. First, and most importantly, I forgot to reset theta dot to 0 at the beginning of each of these experiments. I also realized I needed to make the figure size a little bit bigger to show all of the wonderful things going on in this graph. Here what we've got is a graph of theta dot versus time for several different pendulum experiments where we release it from a different initial angle each time. For the smallest ones, blue and orange, you get what you would expect. Orange, you get this oscillation. Blue, you get a flat line, right? Because it's in equilibrium there. As you increase it, though, this thing starts to sort of perturb away from a sine function. So like, for example, when I get to the red, when I get to theta equal to 1.5, that's where it starts to get this sawtooth type shape. The purple one here even more sawtooth. Then the brown one, theta equal to 2.5, is where it starts to get this kink in the middle, right? Where it's kind of bending there in the middle. Definitely not a sine curve anymore. And then by the time we get to the purple here, theta equal to 3, is where you start to get this interesting little spike pattern that we were observing earlier. So it looks like the interesting transition is going to happen sometime between purple and pinkish purple, so 2 to 3. Why don't we zoom in on that a little bit? Let's go from 2.0 up to, let's still go to 99% of pi, and let's make this in steps of 0.2 now. And we'll take this thing a second to run because it's having to go through all of those experiments each time. Okay, this is cool. This is where we start to see going from 2 to 3 as it broadens out. It looks like it's doing an MC Hammer dance across the graph here. Yeah, so you really start to see this kink develop here. It looks like it develops between 2.6 and 2.8. That's really cool there. The last thing we should take a look at is this funny behavior that I found in the acceleration magnitude on AlgoDo. I've gone ahead and set that up for you off camera. So here we've got the calculation of the acceleration magnitude. Now again, this is the magnitude of the linear acceleration vector, the d squared position vector by dt squared magnitude. That's the thing we're looking at here. We worked this out earlier in an earlier video, and so I've just recreated that equation right here. So I've set this up as an acceleration magnitude list. Now I want to see where this funny business with this extra bump in the acceleration magnitude shows up. So in order to do that, I've set up a loop here for the length of the pendulum. So we're going to keep our initial theta and our initial theta dot the same. I've set up theta to be just north of pi over 4. So we were finding the behavior around 45 degrees earlier. And so now we're going to loop over the pendulum length to see at what point it sets in, because we're going to see that it depends on the initial angle and on the and on the length of the pendulum. So when we run this, this is what we get. So each one of these graphs represents a different pendulum experiment for a different length of the pendulum, all starting with the same initial conditions otherwise. So we go from a length of 1/2 up to a length just north of 1. And so what I end up getting is really interesting. For a length of 1/2 here, those two oscillations are about the same size, right? So we've got this oscillation pattern going on here. Those two oscillations are about the same size. When we get to length of 0.65 though, one of those oscillations starts to die down. So this secondary maximum becomes much lower than the primary maximum. That gets even more exaggerated at L equals 0.8. It's barely a blip here. By the time we get to L equal 1.1, it's hardly there at all. And so this is what we saw in AlgoDo. It does happen there in the acceleration. It really shows you just how rich and interesting this pendulum problem really is.